Good evening everyone. So today we are going to start a new module which is about eigenvalues and eigenfunctions. So the larger aim is to solve a specific class of PDEs, partial differential equations, which can be solved using the techniques of ordinary differential equations. So before moving to the PDEs, we need to introduce the concept of eigenvalues and eigenfunctions. So recall that initial value problem is defined as follows, where the initial conditions or the conditions are defined at a single point only. For example, y of 0 and y dash 0. And in case of boundary value problem, they are defined at two different points, which means they are two different endpoints, y of 0, y of pi, for example, in this case. So to understand the concept of eigenvalues and eigenfunctions, we need to find the non-trivial solution for the given boundary value problem. So now the values of the lambda for which non-trivial solution exists would be known as eigenvalues, and those non-trivial solutions would be called as eigenfunctions. Here lambda is a constant. Now you can easily observe that the solution of this equation depends on either lambda is negative or positive or 0, because you will get the distinct roots or equal roots or complex roots. So let's consider lambda is less than 0. For lambda less than 0, if I take lambda is equal to minus alpha square because it's negative, then the auxiliary equation gives me m is equal to plus minus alpha, which means the general solution is c1 e raised to alpha x plus c2 e raised to the power minus alpha x using the method of undetermined coefficients. Now I use my condition. So y of 0 is 0 gives me, if I substitute y of 0 is equal to 0 here, then this gives me c1 plus c2 is equal to 0, or I can say c1 is minus c2. It means my y of x is minus c2 e raised to the power alpha x plus c2 e raised to the power minus alpha x. Now the other condition which is given is y of pi is equal to 0. That gives me c2 and e raised to the power alpha pi or minus plus e raised to the power minus alpha pi is equal to 0. Now clearly e raised to the power alpha pi plus e raised to minus alpha pi is non-zero. That gives me c2 is equal to 0. Exponential function are always non-zero. So that gives me c2 is equal to 0. Now since c2 is equal to 0 and c1 is 0, it means for lambda less than 0, we get trivial solutions only. But we are looking for non-trivial solution. Next case is lambda is equal to 0. That gives me y1 is equal to c1x plus c2. Now y of 0 is equal to 0, so this is 0. I put x is equal to 0, that gives me c2 is equal to 0. It means y is c1x. Y of pi is equal to 0 gives me 0 is equal to c1 pi, that gives me c1 is equal to 0, implies trivial solution. Yes. Last case is lambda greater than 0. In that case auxiliary equation would be complex roots, and that's why solution would be c1 cos alpha x plus c2 sin alpha x. If I consider y of 0 is equal to 0, so that gives me 0 and c1 cos 0 plus c2 and sin 0 is 0. So that gives me c1 is equal to 0, implies y of x is c2 sin alpha x. Now y of pi is equal to 0, that gives me c2 sin alpha pi is equal to 0. Now c2 is equal to 0 gives trivial solution. Yes. So therefore for non-trivial solution, because both the choices are open, either c2 can be 0 or sin alpha pi is 0. So for non-trivial solutions, we consider C2 to be non-zero, that gives me sine alpha pi is equal to 0, which gives me alpha pi is equal to n pi, or that gives me alpha is equal to n, where n is plus minus 1 plus minus 2 and so on, and lambda is n square, which is 149 and so on, or lambda is alpha square. So the values of lambda for which the given equation has non-trivial solution are called eigenvalues, and corresponding solutions are called eigenfunctions. So for the given equation, the eigenvalues are 1, 4, 9, 16, and I got y of x. Here I got y of x to be C2 sine alpha x. So if I substitute the value of alpha, then this would become the eigenfunctions. So therefore eigenfunctions would be sin x, sin 2x and so on. And clearly a constant multiple of eigenfunction is also eigenfunction, because it would remain a solution. That's why it is not, we are not writing it as C2 sin x or C2 sin 2x and so on. Okay, let's try one more question. Y double dash plus lambda y is equal to 0, y of L is 0, y of minus L is 0, where L is greater than 0. Now again I have to consider three cases for this equation. For lambda less than 0, the solution would look like this. Now y of L is 0 and y of minus L is 0. That gives me a homogeneous system of equation C1, C2, because directly I cannot say anything about the values of C1, C2. Yes, I can compute the value of C1 and then put it into the other equation and so on, but better to see it as a homogeneous system of equations C1 and C2. And clearly, if the determinant of the matrix, or if the matrix e raised to power alpha l, e raised to power minus alpha l, e raised to power minus alpha and e raised to power alpha l, if this matrix is invertible, then we'll get the unique solution, which is C1 0 and C2 0. Yes, and I know that if I compute its determinant, it comes out to be e raised to power 2 alpha l minus e raised to power minus 2 alpha l, which is for sure non-zero. It means that the system of equation has unique solution and it is a homogeneous system of equations. So C1 0, C2 0, it means we will get the trivial solution. If you consider the other case, lambda is equal to 0, then you will get the following two equations A and B. If you add them, that gives you C2 0, and by subtracting them or substituting the value of C2, you will get C1 equal to 0. So again, trivial solution. So the last case is lambda greater than 0, that gives you y of x is C1 cos alpha x plus C2 sin alpha x. If you substitute the value, then again you will get a homogeneous system of equation. Yes. Now this homogeneous system of equation may have trivial solution or non-trivial solution, which means the unique solution or infinitely many solutions. But if we consider the unique solution, then the problem would be that again we will get the trivial solution, but we are looking for the non-trivial solution. Yes, so it means that for the non-trivial solution, I must consider the determinant of the matrix to be 0, because if the determinant of the matrix is non-zero, then we will get the trivial solution. So for the non-trivial solution, we consider the determinant of this matrix to be 0. So if you consider the determinant of this matrix to be 0, that gives you sine 2 alpha l is equal to 0, and that gives you alpha is equal to n pi by 2l. So these are the required eigenvalues. But the question comes that how do I compute the eigenfunction? Because this is my y of x. So from here the eigenfunction is not directly visible. So what I do is that in equation 1 and 2 I substitute the value of alpha, because I got the value of alpha. So this gives me equation 3 and 4. Now for any value of alpha, it has a non-trivial solution. or it has infinitely many solutions. So infinitely many solutions means that, especially in case of two variable, there should be two parallel lines, and it means that we need to find, or we need to consider any value of c1 and c2 which is satisfying either equation 3 or equation 4. So for example, if I choose equation 3, then for the equation 3, if I consider c1 as minus sine n pi by l and c2 as cos n pi by l, it's n pi by 2. So c1 as minus sine n pi by 2 and c2 as cos n pi by 2. So if I take c1 as sine n pi by 2, c2 as minus cos n pi by 2, satisfy equation 3, or you can consider equation 4, doesn't matter. Once you consider this one, then you put it back the value of c1 c2 here, c1 c2 here for the eigenfunctions. So when you put it back, it becomes sin a cos b minus cos a sin b, which is sin a minus b, and these are the required eigenfunctions. So based on the similar approach, you can try one question by yourself. Y double dash plus lambda y is equal to 0, given y dash pi is equal to 0 and y dash minus pi is equal to 0. So let's consider the last question, where you have given an equation x square y double dash minus 3xy dash plus lambda plus 4y is equal to 0, provided lambda is greater than 0. Now we have seen how do we find the eigenvalues and eigenfunctions for the equation with constant coefficient. So it means that to address this problem, first we must transform into equation with constant coefficient, which we have already done. So this is a Euler equidimensional equation. It means if you substitute x is equal to e raised to the power z, then it becomes an equation with constant coefficient d2y by dz square minus or plus p minus 1, so minus 3 minus 1 plus qy is equal to 0. From the auxiliary equation you get the roots 2 plus minus I root lambda. Now it's very easy, you just write down the solution and compute the value of y of x. Now you use both the conditions, which is y of 1 is 0 and 2 plus root lambda y of e minus e y dash e is equal to 0. So y of 1 is equal to 0 gives you c1 0. That means the solution would be c2 x square sine root lambda log x. Now you need y dash e. So you compute y dash e and y of e and use the condition which is given, 2 plus root lambda y of e minus e y dash e is equal to 0. That gives you c2 e square root lambda sine root lambda minus cos root lambda is equal to 0. Now for the non-trivial solution, you must consider c2 to be non-zero. That gives you tan root lambda is equal to 1, or root lambda is 4n plus 1 by 4 pi. That gives you the required eigenvalues, and when you put the value of eigenvalue into y of x, that gives you the required eigenfunctions. So in the next class, we will see how we use the concept of eigenvalues and eigenfunctions to solve the PDEs.